So there's a lot of really cool things that we could say about Fibonacci numbers. One interesting thing that popped up in our warm-up problems is this surprising fact, which is that we can use Fibonacci numbers as sort of a quick reference to help us convert from miles into kilometers and vice versa. So it turns out that if you look at the Fibonacci sequence, which of course is the recursive sequence starting with 0 and 1, and then followed by each next number in the Fibonacci sequence is just a sum of the two prior numbers. So 0 plus 1 is 1, then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. We get the Fibonacci sequence, a very famous sequence in math that kind of pops up in a lot of different places. And what we saw in the warm-up is that consecutive Fibonacci numbers, two Fibonacci numbers that are right next to each other, give us a nice way to convert from miles to kilometers. So 3 miles is approximately the same as 5 kilometers. 5 miles is approximately the same as 8 kilometers. 8 miles is approximately the same as 13 kilometers, and so on. And so this gives us a nice way to start in miles and get to kilometers, or go backwards, right? If you have something in kilometers and you want to know how many miles it is, go to the prior Fibonacci number, right? So 34 kilometers should be 21 miles, and so on. And you might at first think, well, that only helps me if I'm converting from a Fibonacci number of miles or kilometers. But actually no, because it turns out that any natural number can be expressed either if it's already a Fibonacci number itself, or it can be expressed as a sum of other Fibonacci numbers. So for instance, let's say you ran an ultra marathon that was 50 miles, for instance. 50 miles can be expressed as, right, 5 plus 5 plus 5 plus 5 plus 5, right? 10 times. And since 5 miles is approximately 8 kilometers, that means 50 miles is going to be approximately 80 kilometers. And you can do this with any sort of thing that you're trying to convert, right? So you could just express it as a sum of Fibonacci numbers and then convert using this trick here. So that's pretty neat. But why does this work, right? It's like a cool little fact, but why? Well, it turns out the ratio of kilometers to miles is roughly 1.609, and we can end up showing that the ratio of consecutive Fibonacci numbers is close to this. Fibonacci numbers. I'm just going to say close, close to this 1.609. And how do we formalize that though, right? Like close why, close how, right? And so it turns out that if we want to actually prove that this is true and that this continues to be true, what we really need to know is we need to know the limit as n goes to infinity of a ratio of two consecutive Fibonacci numbers. So it helps to give these names. Often we use f sub n to represent a Fibonacci number. So if I want two consecutive Fibonacci numbers, maybe I'm looking for something like f sub n plus 1 over f sub n, in order to say like the ratio of a larger Fibonacci number over the one directly below it, right? The one that comes directly before it. And so if we can show that this limit not only exists, but that it is roughly equal to this 1.6 that we're looking for, that would justify why we're seeing this fun little fact about Fibonacci numbers and the miles to kilometers conversion. So let's see if we can justify this. First, we should define this a little bit more carefully. So we're going to say f sub n is a Fibonacci sequence. We start with f0 being equal to 0, f1 being equal to 1, and any further member of the sequence is defined as fn plus 2 is equal to fn plus 1 plus fn. And that's for any n greater than or equal to 0. Okay, so we are interested in finding the limit as n goes to infinity, if it exists, of fn plus 1 over fn, of that ratio. The theorem that we're going to try to prove is that this sequence that this sequence converges, and that the limit is actually equal to a very important constant in math, which we usually use phi to represent. That's a Greek letter phi. And it's equal to 1 plus the square root of 5 over 2, which seems like it kind of comes out of nowhere, but you'll see that it actually kind of makes sense. Where where that constant comes from. You might recognize that constant, by the way, which is often called the golden ratio. So let's try to prove this. So we know that for any n greater than or equal to 1, we have that f of n plus 1 is going to be equal to fn plus f of n minus 1. This is just the same recurrence relation that we defined up above, but just sort of shifted down 1. What we can do then is, as long as f sub n is at least 1, as long as it's non-zero, which it will be when n is greater than or equal to 1, we know that f sub n is greater than or equal to 1, so we can divide by f sub n on both sides without worrying about dividing by 0, and that's going to give us fn plus 1 divided by fn is equal to fn divided by fn plus fn minus 1 divided by fn. Right, so let's rewrite this. We have fn plus 1 divided by fn is equal to fn divided by fn, which is just equal to 1, plus f of n minus 1 over f sub n. So we're going to let this ratio here on the left-hand side, we're just going to give that a name. We're going to call that r sub n. And so let r sub n be the ratio of fn plus 1 to fn, so that we can just call the left-hand side r sub n here. So r sub n is equal to 1 plus this ratio, which almost looks a little bit like Rn, right? Except it's flipped upside down for starters, and also the index is 1 off, right? Instead of being Fn over Fn plus 1, it's Fn over Fn minus 1. But really that just means that because R sub n is equal to Fn plus 1 over Fn, then R sub n minus 1 is equal to F sub n plus 1 minus 1, which is just Fn, over F sub n minus 1. And so now we can see that this is just the reciprocal of this, which means we can rewrite this as R sub n is equal to 1 plus 1 over R sub n minus 1. Okay, now, supposing that the limit of this R sub n sequence, the sequence that we're looking for at the beginning of the ratio of Fn plus 1 to Fn, so let's just suppose for a second, I'm going to put a star here, suppose that this limit exists. Right, Rn is just another name that I gave for this sequence. So this is a limit that we're trying to prove is equal to phi. Suppose that it exists. Okay, then taking this equation up above, let me call it double star, because I already used star. So supposing that that limit exists, then we can take the limit as n goes to infinity on either side and get this. Okay. Well, as long as that limit exists, we should be able to call it a name. And what we have here then is that the limit on the left-hand side is just L, and the limit on the right-hand side, based on some limit laws that we saw in previous sections, is going to be equal to the limit as n goes to infinity of 1 is just 1, and the limit as n goes to infinity of 1 over this same sequence, r sub n minus 1. Even though the index is off by 1, as n goes to infinity, that's still going to be approaching that same L. Right? We saw already that this is going to approach L, which means the whole left-hand side is going to approach 1 plus L. Oops. Should have been the same color. Okay. Whoops. Is that right? That's not quite right. It's not going to approach L itself, but it'll approach 1 over L, right? Because the denominator is going to be heading towards L as n goes to infinity. Okay. So what does this mean? Well, if L is equal to 1 plus 1 over L, I can multiply by L on both sides. It's not going to change anything, and we'll get L squared is equal to L distributing here plus 1 over L times L is just 1. And I can solve this now for L. This is just a regular old quadratic equation. L squared minus L minus 1 is equal to 0. And using the quadratic formula to solve for this, I'm going to get that letting my a be equal to 1, my b be equal to -1, and my c be equal to -1, the quadratic formula tells me that L should be equal to the opposite of -1, which is +1, plus or minus the square root of -1 squared minus 4 times 1 times -1, all divided by 2 times 1. And what does this simplify to? Well, it simplifies to 1 plus or minus the square root of 1 plus 4, which is 5, over 2. And hey, that looks like something that we were working with up above, right? That looks like what we were trying to show. We wanted to show that this converges to the limit L of 1 plus the square root of 5 over 2. That's basically what we got here, except we technically got two answers here, right? We got 1 plus or minus. So how do we know which is the correct limit, if any, if we're getting two different values here? Well, we just need to keep in mind, remember that this limit is always going to, this expression here, every element of this sequence, fn plus 1 over fn, that's always going to be positive, because fn plus 1 is always going to be greater than fn. These are all positive numbers. Like this fn plus 1 over fn is guaranteed to be somewhere between 1 and 2, just because of the way that the fn plus 1 is defined, right, as fn plus fn minus 1. Which means this value has to be between 1 and 2. We'll use that in the next proof as well. And so what that means is that we can sort of throw away the negative root here and say that actually L has to be equal to 1 plus the square root of 5 over 2. Great, that is what we were trying to show, right? And this is what we define to be our phi. That's what we call phi, the golden ratio. Okay, excellent. So that completes our proof, right? Almost, except for that one little asterisk that I haven't addressed here, right? That suppose that the limit actually exists. That's kind of a big suppose, right? So we need that to be true, right? We need that limit to exist in order for the rest of the proof to follow. And it turns out to be kind of tricky to justify. It takes a little bit of work to justify. So I'll try to outline that here. And some of the proof of this I'll leave to the exercises. Some of the little parts I'll leave them as kind of lemmas that we'll prove in the exercises. But this is what we're claiming as sort of a lemma to our larger proof, that for the Fibonacci numbers fn, if R sub n is the sequence of ratios that we defined in the proof up above, then that sequence is actually going to converge to some limit L. And once we've proven that, our previous work will allow us to conclude that that L must be the golden ratio, right? That phi, 1 plus square root of 5 over 2. So how do we prove this? So first note that if R sub n is equal to fn over fn minus 1, right, it's a ratio of Fibonacci numbers, then we can observe that any two consecutive numbers in this sequence are going to have a distance apart that is getting smaller, right? It's getting close to 0. So let's actually prove this. Rn plus 1 minus Rn, the difference between two consecutive terms in this sequence is going to be fn plus 1 over fn minus fn over fn minus 1. That's just by plugging in the definitions of Rn plus 1 and Rn. And so if we combine these to one fraction by getting a common denominator of fn minus 1, this is going to look like fn plus 1 fn minus 1 minus fn times fn, right? This fn times the denominator here, fn, all divided by the common denominator of fn minus 1. Okay, so does this make sense so far? All right, I think this makes sense. Now, I claim that this is actually going to be getting close to 0. It's going to be approaching 0. And to prove that, we need to use this sort of interesting identity of Fibonacci numbers, and I leave this to the exercises. We'll see later. But it states that if you take, for any Fibonacci numbers, fn, that fn squared minus fn minus 1 squared minus fn minus 1 is going to be equal to -1 to the power of n minus 1. In other words, if you take any two consecutive Fibonacci numbers, you square the larger one, subtract the square of the smaller one, and subtract the product of the two Fibonacci numbers, you're always either going to get -1 or +1. Kind of a a funny thing, a little bit surprising, but you can prove it by induction, and we'll do that in the exercises. In particular for us, that means we're going to be able to look at our numerator here and use this identity to show that that numerator is going to be approaching negative 1 to the n. Okay, so how do we do that? Well, let's look at our numerator. Our numerator, which is fn plus 1 times fn minus 1 minus fn squared. We're going to be able to apply that identity, assuming that it's true for now, to simplify this as negative 1 to the n. Okay, so to do that, notice that we can use the recursive definition of fn plus 1 to rewrite that first term as fn plus fn minus 1. We're still multiplying that by fn minus 1, and we're still subtracting fn squared. Now from here, if I were to expand this out, redistribute this out, we get fn times fn minus 1 plus fn minus 1 times fn minus 1, so fn minus 1 squared, and then minus fn squared. And now we see how this is starting to look like our identity up here. The only difference, I suppose, is that it's sort of the opposite, right? It seems like it's been multiplied by negative 1. Up here in our identity, we have our fn squared first, and so we can sort of pull out a negative 1 here and rewrite this whole thing as fn squared minus fn minus 1 squared minus fn times fn minus 1. And now our identity applies right away. So inside the parentheses, by our identity, this is equal to negative 1 to the n minus 1. And when we multiply negative 1 to the n minus 1 times another factor of negative 1 to the 1 power, this really is equal to n copies of negative 1. So negative 1 to the n power. Which means our ratio up here, this ratio, can now be rewritten using this identity as saying that Rn plus 1 minus Rn plus 1 minus Rn. The distance between them is going to be equal to negative 1 to the n times the denominator from up above, which was fn minus 1. N minus 1. Apologies. Okay, so what does this mean? What does this tell us? Well, as n goes to infinity, that denominator is going to be getting large. We're multiplying two larger and larger Fibonacci numbers, and the numerator is going to be negative 1 to an nth power, but in particular, it's going to be staying relatively small compared to the denominator. And so that tells us that the differences between these consecutive terms is going to be approaching 0 as n goes to infinity. Okay, now that doesn't necessarily mean that the limit exists, but we'll try to use this same idea, looking at some subsequences, to determine that the limit does in fact exist. So let's see if I give myself space on the next page. Okay, so we still must show that the limit of the sequence exists. And to do that, we're going to look at two different subsequences. We're going to call one the even subsequence, and we're going to call the other the odd subsequence. So essentially what we're looking at with the even subsequence is what we're calling, I guess it would be, if R sub n is equal to fn over fn minus 1, really this even subsequence that we're looking at is going to be R2, R4, R6, and so on. So we're just picking out every other term of the original sequence starting at the R2 term, whereas the odd subsequence is going to start with R1, R1, R3, R5, and so on. So it's every other term starting with R1 instead of starting with R2. Okay, now we're going to show that each one of these subsequences is converging, and then we're going to put those two pieces together along with what we just showed in order to show that the entire limit must exist. Okay, so let's start with the even subsequence, and I'll leave the odd subsequence as another exercise because it's pretty similar. So in that first case, I'm going to claim that this subsequence here, this even subsequence, is actually an increasing subsequence, right? So I'm going to show that f2n over f2n minus 1 is less than f2n plus 2 over f2n plus 1. That is to say, I'm going to show that r sub 2n is less than r sub 2n plus 1. In other words, if I'm looking at this subsequence of every other element of my original sequence, all with the even indices, that it's going to be an increasing subsequence. So to show that, we really want to use that same identity that we mentioned earlier, right? So we must show that f sub 2n over f sub 2n minus 1 is less than, oops, sorry, rewrite that. Maybe a better way to write this. I'm gonna rewrite it, bringing things over to the other side of the equation. So moving this to the right-hand side, really what I want to show is that f2n plus 2 over f2n plus 1 minus f2n over f2n minus 1, I want to show that that's going to be greater than 0, and that'll be enough to show that this even subsequence is a strictly increasing subsequence. So to do that, we're basically doing the same thing that we did before, right? First, I'm going to take that left-hand side and I'm going to combine it into a single fraction. So we have that this expression, the left-hand side, is equal to, combining them into one fraction, I want to get a common denominator of f2n plus 1 times f2n minus 1. So multiplying the first fraction on the top and the bottom by f2n minus 1 gives us f2n plus 2 times f2n minus 1. Multiplying the second fraction on the top and the bottom by f sub 2n plus 1, we'll have f2n plus 1, all divided by that common denominator of f2n plus 1, f2n minus 1. All right, so what do we do with this? How do we show that this is always going to be positive in order to show that this is an increasing subsequence? Well, again, we're just going to apply what we know about Fibonacci numbers using their recursive definition. I'm going to rewrite each of those highlighted terms using the recursive definition of Fibonacci numbers. So f2n plus 2 is just the sum of the previous two Fibonacci numbers. That is f2n plus 1 plus f2n. That would be the previous two terms. And that's being multiplied by that f2n minus 1 term. On the right here, we still have an f2n, but I'm going to rewrite f2n plus 1 as the sum of the previous two Fibonacci numbers. That is f2n plus f2n minus 1. Still over the same common denominator. All right, now what? Make ourselves a little bit more space here. If we were to actually distribute these out, we'll see that we'll have cancellations here, because we'll have 2n minus 1 times 2n plus 1, f2n times f2n minus 1, then we'll subtract f2n times f2n minus 1 as well, right? In other words, this times this minus this times this are going to cancel each other out, and all that will be left is the product of these two and then the product of these two. So we'll be left with f2n plus 1 times f2n minus 1 minus f2n times f2n, right? f2n squared, basically. All divided by f2n minus 1, f2n minus, oops, that should have been a plus 1 and a minus 1 here. Okay. Well, then what does that numerator simplify to? We actually showed in the last proof that this numerator is going to simplify to -1 to the 2n power. You can go back to the last slide and see that that's exactly what we showed when we were looking at the original differences between two elements of our original sequence. But that same identity that we saw before allows us to show that the numerator is equal to -1 to the 2n power divided by f2n plus 1, f2n minus 1. And why is that going to be positive? Well, -1 to an even power is just going to be equal to 1 on top. and f2n plus 1 times f2n minus 1, right? These are just, oh, sorry, that's a minus 1, but either way, these are just two positive numbers being multiplied together. So certainly the denominator is positive as well, which means this entire thing is going to be greater than 0, which is what we wanted to show in the first place. Great. What does that tell us, right? Where do we go from here? That just means that this is going to be an increasing sequence. So the even subsequence is an increasing sequence. We also know that it's bounded above. In fact, the entire original sequence is bounded above. We said this before. It's bounded above by 2 because we're taking the ratio of two consecutive Fibonacci numbers, fn plus 1 over fn, and fn plus 1 is just fn plus fn minus 1, and so that's going to be bounded above by 2. And so what do we know? Well, then we know that because it's an increasing sequence, which is bounded above, that this is going to be, by the monotone convergence theorem, it's going to have some limit. It's going to converge. So by the monotone convergence theorem, this even subsequence converges to some limit L. We'll call it, well, actually, let's call it L sub E for an even subsequence. All right, great. Now, there's a whole second part of this which is almost identical, except it's kind of going in the other direction. So then what we have to do in the exercises is to show that the odd subsequence, on the other hand, is a decreasing subsequence, which is bounded below by 1. So again, by the monotone convergence theorem, we'll see that this is, because it's decreasing and because it's bounded below, it's also going to converge to some limit L0, or I should say L sub O. Some limit L sub O for L sub odd, the odd subsequence limit. Could these two limits, L sub E and L sub O, be different from each other? It turns out that no, and that's because we had originally showed that the distance between two consecutive numbers in our original sequence is going to 0. So from here we can say that since we had shown that r sub n plus 1 minus r sub n is going to approach 0 as n goes to infinity, right? These two consecutive numbers of the sequence are getting arbitrarily close together, and so there's no way that this even subsequence and the odd subsequence could be going to two different limits, because these are sort of being spliced together into the larger sequence, and the distance between them is going to 0. So that means that our odd and our even subsequence are actually equal to each other, and therefore the limit of the sequence is going to exist. Putting that together with what we showed on the last slide, that means that that limit must be equal to that golden ratio phi of 1 plus the square root of 5 over 2. Now we can put all of the pieces together. Oops, we already talked about that a little bit. And we can say that since the ratio of consecutive Fibonacci numbers is approaching that phi, which is 1 plus the square root of 5 over, square root of 5 over 2, and that's approximately equal to, what is that? I think it's like approximately equal to 1.6. There's more, right? So phi is an irrational number. It's going to go on forever, but we'll say it's approximately equal to 1.6, which is very close to that conversion factor of kilometers to miles. Oh, I'm sorry, it's 1.618. I knew it was in there somewhere. Okay, that's very close to the conversion factor that we had said was 1.609. And so that's why we end up getting that really cool fact about the conversion factor for kilometers to miles being similar enough to the ratio of Fibonacci numbers that we can use those Fibonacci numbers as a shortcut, which is cool. All right, so to wrap this up, I just want to point out that the Fibonacci example illustrates kind of a broader theme here, which is that patterns that we can notice informally can be made more rigorous by looking at limits. We're going to explore this a little bit more in the exercises by looking at function tables. For instance, if middle schoolers looked at this function table below, maybe you don't call it x and f of x, maybe you call it x and y, or inputs and outputs, but they should be able to see that this is a linear function by looking at the difference between outputs, right? So from 2 to -1, our inputs went up by 1, but our outputs went down by 3. Then it went down by 3 again, down by 3 again, right? And seeing this -3 here is enough to say that, that this is going to be a linear equation, provided this continues in this manner, that this is a linear function whose slope or whose rate of change is -3. But in the exercises, we're going to look at some more complicated examples and try to deduce patterns that may be useful for secondary math students, but whose explanations really lie in their limits.